Welcome to this enlightening video, where we embark on a journey into the forefront of environmental innovation, carbon capture and storage (CCS) techniques. As the specter of climate change looms large, the need for transformative solutions becomes more urgent than ever. This video is your gateway to exploring the ingenious strategies that hold the potential to revolutionize the way we combat carbon dioxide (CO2) emissions and safeguard our planet's future. From the ingenious concept of direct air capture (DAC), where technology plucks CO2 from the very air we breathe, to the intricate synergy of bioenergy with carbon capture and storage (BECCS), which seeks to harness nature's own processes for carbon sequestration, we'll journey through a landscape of innovation that promises to rewrite the rules of sustainable living. Venturing deeper, we'll delve into the world of mineralization and enhanced weathering, techniques that mirror the Earth's natural carbon cycles, but with a twist of human ingenuity. These methods not only capture CO2, but also transform it into stable compounds, effectively locking it away for centuries. But as with any revolutionary endeavor, challenges abound. We'll unravel the complexities surrounding these techniques, the energy demands, the economic viability, and the regulatory intricacies that shape their feasibility on a global scale. It's a holistic exploration that doesn't shy away from addressing the potential environmental impacts of these transformative solutions, be it in our oceans or within the concrete foundations of our cities. Join us on this voyage of discovery, where science, innovation, and sustainability converge. Together, we'll uncover the intricate tapestry of ideas that could alter the trajectory of our planet's destiny. As we stand at the crossroads of possibility, let's harness knowledge, foster dialogue, and pave the way for a greener, more sustainable world. Welcome to the future of carbon mitigation. Let's begin. Carbon capture and storage (CCS) is a set of techniques aimed at capturing carbon dioxide (CO2) emissions from various sources, such as power plants and industrial facilities, and then storing the captured CO2 in geological formations or other suitable repositories. CCS plays a crucial role in mitigating the effects of climate change by reducing the amount of CO2 released into the atmosphere. Here are some innovative CCS techniques. Direct air capture (DAC). DAC involves capturing CO2 directly from ambient air, even in locations where there are no concentrated sources of emissions. Large fans pull air through a filter material that chemically binds with CO2. The captured CO2 can then be processed and stored underground. DAC has the potential to address emissions that are difficult to mitigate using traditional CCS methods, but it currently requires substantial energy input and cost reductions to be more widely adopted. Bioenergy with carbon capture and storage (BECCS). BECCS combines biomass energy production with CCS. Plants, like trees and crops, absorb CO2 from the atmosphere during their growth. This biomass can be burned for energy, and the resulting CO2 emissions can be captured and stored. The net result is a negative emission process, where more CO2 is removed from the atmosphere than is emitted during energy generation. Mineralization. This technique involves accelerating the natural process of mineral weathering, where certain minerals react with CO2 to form stable carbonate compounds. This process can be artificially enhanced by grinding down suitable minerals, mixing them with CO2-emitting flue gases, and allowing the chemical reactions to take place. The resulting carbonate products can be stored in geological formations. Enhanced weathering. Similar to mineralization, enhanced weathering involves exposing large quantities of minerals, such as olivine, to CO2-rich environments. These minerals react with CO2 to form stable carbonates. The technique can be applied in natural environments like beaches or in controlled facilities. However, large-scale implementation and environmental impacts need careful consideration. Ocean-based CCS. This approach involves injecting liquid CO2 deep into the ocean, where it dissolves and is stored as dissolved inorganic carbon. While this can be effective in terms of CO2 storage, it raises concerns about potential environmental impacts on marine ecosystems and the need for thorough risk assessments. Carbon mineralization in concrete. Carbonation of concrete is a natural process that can be accelerated in controlled conditions. By exposing concrete to CO2, it undergoes mineralization, which helps lock in the carbon and make the concrete more durable. This approach has potential in both construction materials and carbon sequestration. Hydrogen-based CCS. By utilizing clean hydrogen for industrial processes and power generation and capturing the resulting CO2 emissions, a cleaner energy cycle can be established. Hydrogen can be produced using renewable energy sources, reducing the overall carbon footprint of the process. It's important to note that while these techniques show promise, several challenges remain, including high costs, energy requirements, regulatory hurdles, and potential environmental impacts. A comprehensive approach to CCS, including policy support, research, and development, is necessary for successful implementation on a large scale.